So now in this lecture we will be dealing with a different chapter, that is chapter number 2, uniform flow. So we will be dealing with uniform flow. I told you regarding the introductory part of uniform flow when we were dealing in the introduction to open channel flow chapter. Fine, there I told you that flow parameters with respect to space, we classified it as uniform flow and non-uniform flow. So specifically in this chapter or in this topic, we will be dealing with your uniform flow. Now, what happens is, I will draw first a figure for you. Suppose this is your datum, this is your datum, and this is your flow which is occurring. This one is your Z1, exactly like what I did in your energy equation. I told you that we will be dealing it in uniform flow as well. So the same thing, V1 square by 2G. Similarly, at this section, you will get Z2. Here this one is Y2 and this one is V2 squared by 2G. This one is your head loss. Fine, this is section 1, this is section 2. Now what happens is, this portion, this line is known as your energy line slope. Energy line slope by SF. Fine. Similarly, this is known as your water surface slope. Water surface slope, which you denoted by SW. Fine. And this one is known as your channel bottom slope. Channel bottom slope denoted by S naught. Some people write it as SB also. So denotion, you should be first knowing what does this means. So denotions you can change by yourself. It is not mandatory that energy line slope you will be writing SF only. You can write SE, but the meaning should be clear to you. Fine. So now I applied Bernoulli's equation. I will do it quickly this time also. So we will apply Bernoulli's equation at section 1 and at section 2. So now applying Bernoulli's equation at section 1 and 2. Fine. So at section 1, the sum of all the heads, that is your potential head, pressure head and kinetic head, that is Z1 plus Y1 plus V1 square by 2G is equal to Z2 plus Y2 plus V2 square by 2G plus head loss. So this is your head loss. Now, I wrote when we were dealing with the energy equation that your Y1 is equal to Y2 and V1 is equal to V2. Because of that, we got head loss as what? We got head loss as Z1 minus Z2. So now, first of all, before dealing it further, let me write the definition of uniform flow. So now, here I will write all the characteristics of uniform flow. A flow is said to be uniform if the flow parameters are constant with respect to what? Your space, or you can say with respect to distance. Now, what are these flow parameters? A flow is said to be uniform if the flow parameters are constant with respect to distance. And what are these flow parameters? This is your, like I told you, their discharge, velocity and your depth of flow. So you can write it here, depth of flow, velocity and your area, cross-sectional area. Cross-sectional area. Fine. Now, I told you that velocity will be equal, because this is your uniform flow, so V1 is equal to V2. The depth will be equal, that is Y1 is equal to Y2. You will get it as Z1 is equal to Z2 plus head loss. Now, this Y1 is equal to Y2, what does this means? That there is a depth, fine, maybe in this figure it is not looking like Y1 is equal to Y2, but you draw yourself, you understood, right? So this constant depth of flow, because you can see what depth is at section 1, exactly the same depth is at section 2, fine. So this constant depth of flow is known as your normal depth. So I can write this, the constant depth of flow in the constant depth in case of uniform flow is known as your normal depth. Normal. Fine, these 2 points are clear to you. Now, this Z1 is equal to Z2 plus head loss. I can write it as head loss is equal to Z1 minus Z2. Fine. Now, suppose the distance between these two sections is L, and I divide by L on both the sides. So, HL by L is equal to Z1 minus Z2. This will give you what? Just tell me. Z1 minus Z2. So this will give you what? Divided by L. This will give you what? This will give you the slope. And what is this slope? This slope is your S0. Now what exactly, this is divided by L. Now what exactly happens is, now as I told you, Z1 minus Z2 divided by L will give you your channel bottom slope, that is your S0. In the case of uniform flow, just remember, in the case of your uniform flow, your channel bottom slope, water surface slope and energy line slope, that is your total energy line. This one is what? This is your total energy line. Total energy line, hydraulic gradient and your channel bottom, they all are parallel to each other. What I said, in case of uniform flow, total energy line, hydraulic gradient line and your channel bottom all are parallel to each other. Fine. In books you can find they have written S0 is equal to SF is equal to SW also. Fine. So we can say total energy line, hydraulic gradient line and channel bottom are parallel to each other. Fine. So these were the characteristics of the uniform flow which you got. Now, can you tell me, you got the slope here, fine. Now, what I am interested in getting in uniform flow, like, because this is a theoretical part which we dealt, but now what is exactly the parameter which I am interested in? Could you tell me? Like whether I am interested in discharge, whether I am interested in velocity, what I am interested in? Come on, tell me fast. Now what is happening is, I told you what are the conditions of uniform flow, what is uniform flow, I told you the characteristic of uniform flow. But now, if I have to design a channel section for uniform flow, I need what? I need the velocity, I need the discharge, I need the area, I need the depth of flow. Fine. So, at least I need any two parameters, like you know discharge is equal to area into velocity. So, if I know the discharge, if I know the velocity, so I can calculate the exact area of the channel section which is needed to be designed. So, basically like you will be knowing the discharge, that's a certain amount, certain Qmax of discharge is coming in that particular channel section. But how to calculate the velocity? The question comes that. So, now all those students who have already studied, they have encountered Chezy's equation, and for all those students who haven't come across this word, you don't have to worry, because I'll derive the Chezy's equations, so that in case of you are having any query that how the end results came, you don't have to worry, I'll derive it for you. But this derivation part is not at all asked in your examination, I'll tell you in advance, fine. So, now Chezy's equation, I'll draw the same diagram which I had drawn while I was dealing with the momentum equation. So, here this is your channel bottom, this one is your, this is hydrostatic pressure which is acting. You know, right, this was at section 1, I hope you remember it. Do revision frequently because this topic is important, and from uniform flow questions has been asked many a time in your examination. Fine. So, you know that this is your bit slope, you can say theta. This one is your total energy line, and this is your V square 2G. Fine. Now, what is happening? This side your hydrostatic pressure force is acting, that is your P1. You can denote it by Fn also, because I don't want that silly doubts you ask me, ma'am, why you have written P1, P is for pressure and F is for force. I told you, you can denote anything. For me, P1 is the pressure force at section 1. I told you earlier also. And this one is your P2, pressure force at your section 2. Now, what is happening? This W weight is acting vertically downwards. So, I will resolve it into two components, that is your W sin theta and W cos theta. Fine. Now, what is happening is, in this section when the flow is occurring from upstream to your downstream side, this is the flow which is occurring, fine, because I told you in the introductory chapter only that in open channel flow, flow occurs under the action of gravity, fine. So, now what is happening? A resistance force will be acting opposite to the direction of flow. So, what is that resistance force? That is your frictional force which is acting, F. So, here also you know that rate of change of momentum is equal to your external force applied, and specifically rate of change of linear momentum is equal to your external force applied. So, what you can see, I will write it here, pressure force at section 1, in case you want to write down the derivation also, section 1, P2 is your pressure force at section 2. Now, what you have to do? P1, I will take this direction as positive, direction of flow I will take it as positive. You can take the opposite also, there is no problem in that, fine. P1 minus P2, and this one is your plus W sin theta. So, this is plus W sin theta, and this is your minus opposite to the direction of flow. So, this is minus times of frictional force. This is equal to your M2 minus M1. Now, till this portion, everything is same what we did in your momentum equation. But there what you assume? You assume that the channel is frictionless and the channel bottom slope is horizontal. If the channel is horizontal basically, so what you said was theta is equal to 0. So sin theta was 0 and you got this component 0. Similarly, you got this component as 0 because you assume that there is no friction which is prevailing. But here we won't do that. In uniform flow, what happens is, you have come across Newton's law of motion, force is equal to mass into acceleration. Fine, you have studied this in your preliminary classes like in your 9th and 10th, fine. Now, this acceleration is basically composed of your convective and temporal. Fine, these are the two acceleration. First one is your convective and second one is your temporal acceleration. Temporal you also call it as local acceleration. Now, in case of your uniform steady flow, what I said, in case of your uniform steady flow, both convective and temporal acceleration is 0, because of which your force, here I have denoted it by F, you can write it by P also, because this is something which you have came across most often. So if I would have written it P, you would have crumbled it out. Fine. So I have written it force is equal to mass into acceleration. Acceleration is composed of convective acceleration and your temporal acceleration. So now I will write for steady uniform flow, sorry, both acceleration are 0. Because of which what happens is your P1 pressure force will equal to P2 and your M1, that is momentum, will be equal to M2. You are getting this? Acceleration composed of two parts. This you would have studied in your FM, fluid mechanics, this part. It's some students don't know what is temporal, so it is local acceleration. Fine. So acceleration composed of convective and temporal. So for steady uniform flow, both acceleration are 0, because of which what you will get, the force, pressure force at the two sections are equal and your momentum is equal. So what is there now? What you have to do? P1 is equal to P2, so this portion you will get it 0. M1 is equal to M2, so this portion will also get cancelled out. So what you will get now? You will get W sin theta is equal to your frictional force. Fine, this W sin theta is equal to your frictional force. Now, two things I will do to make this expression more precise. First thing, you know that gamma is equal to weight upon volume. So now weight can be written as gamma into volume. And what can you write this volume? Suppose this distance to be L and the cross sectional area is A. This is your cross sectional area. So what you can write volume? You can write volume as A into L. That is, you can write weight as gamma A L. Getting it? So W is equal to weight, you have written it gamma A L. So gamma A L sin theta is equal to your frictional force. Now, if I assume this theta to be very small, that is sin theta is equal to your tan theta, which is equal to your S naught, that is your channel bottom slope. So, if theta is very small, that is theta is equal to sine theta is equal to tan theta. Fine, which is equal to your S naught. So now you will get it what, in place of sine theta you can substitute S naught. Fine, so what you will get, theta is very small, sine theta is equal to this one. Gamma AL S naught is equal to your frictional force. From here you got a result, that is gamma AL S naught is equal to your frictional force. See, I just want you that what happens is questions can be asked, because you can predict the questions. You don't know that exactly this question will be asked. They can give you 4 different expressions for your frictional force. But if you would have understood the definition, I am not telling you to mug it up. Fine, if you have understood the definition and you have seen this expression, normally that 1 marks question you will be able to attempt it. Fine, so from here you got frictional force is equal to gamma AL S naught. Now, I am interested that I have to calculate the velocity. I told you earlier that you would be given a certain amount of discharge is flowing through a channel, but I need to calculate what will be the velocity. So, for calculating the velocity, till now I haven't got any term regarding the velocity. So, what can I do? I need to substitute something in place of this frictional force for getting the velocity. So, now let us look what can I do. Now, just look at this diagram. This frictional force is acting along this channel section. Fine. If this frictional force is acting, normally there will be a shear stress which is also acting on the wetted perimeter. Like I will draw this. This is your section, somewhat like this. Fine. So now what is happening? This is your whole perimeter. This is your perimeter. And now if tau naught is the average shear stress, average shear stress acting on the wetted perimeter. Fine. This is your tau naught, which is the shear stress which is acting along the wetted perimeter. And what is your wetted perimeter? Length of the boundary of the channel section in contact with water. I already told you the definition when we dealt in introduction to open channel flow, your geometric parameters. So now, if tau naught is the shear stress which is acting on the wetted perimeter, normally you told that there is a frictional force which is acting. So this basically, to be precise, this frictional force is your drag force. Fine. And in drag force you have studied 2 types. One is your pressure drag and the second one is your skin friction drag. So here in this case, basically your skin friction drag will be acting. So can you write, but here you can denote it by Fs also, or if you are writing drag force you can write it by Fd also. But since I have taken it here frictional force only, so I will denote it by Ff. Fine. This is acting along the wetted perimeter. So this one is your P, which is your perimeter, fine, and your length. So I have written tau naught, which was your shear stress, average shear stress acting on the wetted perimeter, is equal to your frictional force divided by, this is one is your area, that is your AS. Fine. You could have written it first, tau naught is equal to Ff divided by AS, skin frictional area, because you know that this is the skin friction drag. So Ff divided by AS, and AS you can write it as P into L. So now from here, from this expression, can I get Ff is equal to, that is frictional force is equal to tau naught PL? Yes, I can get. So can I substitute this value tau naught into P into L in this expression? Of course I can do. Fine. So what I can do is gamma AL S naught is equal to tau naught PL. So what you will see, this L and this L will get cancelled out. I will solve it here. After this, what you will get it as gamma, this which is there in multiplication with tau naught, I am putting it in division, that is A by P S naught is equal to tau naught. Do you memorize what is this A by P? Don't tell me you have forgotten, just tell me. A by P is what? This is your wetted area by wetted perimeter, and that is what? It is your hydraulic, come on, it is your hydraulic depth or radius? Hydraulic radius. Fine. So I can write tau naught is equal to gamma R S naught, or you can simply write tau naught is equal to gamma R S. This is an important result because we will be solving numericals also on this. So tau naught is equal to gamma R S naught is the average shear stress on the wetted perimeter which is acting. Fine. But till now I did two things, I got two end results, but till now I haven't got the expression for velocity. So now we will proceed. Tau naught is equal to gamma R S naught, this you know. Shall I do it here? Now, based on experimental studies, what I said, based on experimental studies, write it that first, based on experimental studies, tau naught is equal to F by 8 rho V square. Now, if you will ask me how you got this, so this is based on experimental studies, fine. So, I can equate this value of tau naught with this value of tau naught which I got. So, now I can put it this equation as second and this one is as first. So, equating equation 1 and 2. What I will get it as? Gamma R S naught is equal to F by 8 rho V square. Now, how can I get the value of velocity? Here you got the term velocity, that means from this expression you are going to get the velocity. But I have to reduce some values, but I am not getting it. What to do? I want to cancel this rho, that is your density, and you have been given gamma, and you know that gamma is equal to rho g. So what you can do is rho g R S naught is equal to F by 8 rho V square. Fine. So what you can see, this row and this row will get cancelled out. Now substitute everything, I just want the velocity only. So what you will get, V square is equal to 8g by F R S naught. Now I want to get the velocity, so I will remove this square, under root 8g by F root over R S naught. Now you will get the Chezy's coefficient, that is V is equal to C root over R S. Fine. This is basically your Chezy's equation which you will use it. Fine. This is important. Whatever things I am marking it in block, you also please mark it in block. As I told you earlier, at the last moment when you will be turning the pages, at least you should memorize these things. So this is your important. V is equal to C root over RS, where what is your R? This is your hydraulic radius, S is your bed slope, or you can say channel bottom slope, and V is your velocity. Now comes what is your C? C is your, I will erase this first. You have written this, right? I am erasing it out. So now V is equal to C root over RS, where V is your velocity, C is Chezy's coefficient, R is your hydraulic radius, and S is your channel bottom slope, or you can say bed slope. Fine. Now, what is the value of C? You can say C is equal to root over 8G by F. This is the value of your Chezy's coefficient. The reason you should know this, because what happens is, somewhere you will be given your F, which is your friction factor, and you will be asked to calculate the velocity with the help of Chezy's equations. So, until and unless in that particular question you know that C is equal to root over 8G by F, you won't be able to solve the questions. Now, coming to the dimensional part of it, what is the unit of your Chezy's coefficient? Come on, you can do it. This is very simple. C is equal to, you know that acceleration due to gravity, what we write it? We write it as meter per second square. This is the unit. And what is this F? I haven't told you what is this F till now. Tau naught is equal to F by 8 rho V square. I wrote it based on experimental studies, where V was your velocity, rho was your density. But till now, you have come across this F, that is your frictional force. But you haven't seen this small f. What is this? Nobody asked me also. F is your Darcy-Weisbach friction factor. What is this F? This is your Darcy-Weisbach friction factor. Now, what is happening? First, let us move with the dimensional analysis. You don't have, because it is a factor, there is no units. You are having a numerical value. So, there will be no unit for this also, and 8 is also just a number. So, no dimensional unit for this. So, on solving this, C is equal to meter to the power half and second. What you will get? You will get the dimensional analysis of C as L to the power half T to the power minus 1. This is the dimensional analysis. If somebody asks you what is the dimensional analysis or what is the dimension of Chezy's coefficient, that is L to the power half T to the power minus 1. This is very simple. Now, what happens is, if you ask me that how you got this tau naught is equal to F by 8 rho V square, because I told you based on experimental studies. This portion, is it clear to you? Before dealing with the part how it came, I want you to write one thing. Here you got the result W sin theta is equal to frictional force. What does this mean? Could you tell me first? What does this mean? W sin theta is equal to your frictional force. What does this mean? I'll tell you. The frictional force which is acting between the fluid and the channel boundary, because you see that there is a liquid, first thing, and there is a frictional force which acts along the boundary of the channel section. So, the frictional force which is acting between the fluid and the channel boundary is balanced by what? This W, and W is your weight, that is your, come on, that is your gravity force. So, you can write in case of uniform flow, because you got this result for what? You got this result for uniform flow. So, I can write it, the frictional resistance acting between the fluid and the channel boundary is balanced by what? It is balanced by gravity force. Is balanced by gravity force. Fine. This is also one of the characteristic of your uniform flow. Now, coming to the part how you got this tau naught is equal to F by 8 rho V square. Now in FM, those students who have studied FM, you have come across the head loss due to friction, HF, right? So could you tell me the expression for your head loss? What expression do you get for your head loss? Can you tell me the expression? What is the expression? Come on, tell me fast. What you get? HF is equal to FL V square upon 2GD. This is the expression which you get for head loss. Now, here this F is your what? This is exactly same this F which I have written, Darcy-Weisbach friction factor, or you have studied its Darcy's friction factor, both are right. Now, how this F is related to your F dash, which is your friction coefficient, because what happens is sometimes in question they'll give you friction factor and sometimes they give you friction coefficient. If you have solved problems in FM, you have encountered this, fine. So if there is F and F dash, then F is equal to 4 times F dash, where your F dash is coefficient of friction also you can say, or you can say friction coefficient. Coefficient of friction, or you can say it as friction coefficient. So from here F dash is equal to F by 4. Fine. Now you have studied boundary layer in your FM, and from there you get a result, and now I won't be teaching you boundary layer and all, and this portion what I am telling you, this is not important, the end result was important. Just for your query, in case how this F by 8 rho V square came, I am telling you that F is equal to tau naught half rho V square. This is your F dash. Fine. This F dash is equal to, this is the friction coefficient is equal to tau naught half rho V square, where V is your average velocity. This came based on your boundary layer. Fine. So from here what you get, there you have written it, fine. So now if I want to get the value of F dash in terms of F, fine, what can I write it here? I can write it as F by 4, because here you can see there is no F dash, there is F, fine. So now this is F by 4 tau naught half rho V square. I am telling you this V is your average velocity, fine. So T naught is equal to F by 8 rho V square. This was the result which I have wrote it here based on experimental studies. In case you have doubt, you can come across this word. Please don't confuse with coefficient of friction, that is your friction coefficient, and what? Darcy's friction factor. Because in FM what you do, many a time you may make mistakes like this. You don't read it every time you take it F, and that is why you commit mistakes, right? So from here, this concept, if somebody is asking, I am telling you this is based on your boundary layer theory. Fine. And so tau naught is equal to F by 8 rho V square. So never mind, you got the end result as V is equal to C root over RS, which is your Chezy's coefficient. Fine. Now in the coming lecture, we will be dealing that how this value of C, because you know that velocity is equal to C root over RS, you got the result. But if we have been given hydraulic radius, we have been given the slope, but we have to calculate the Chezy's coefficient. How can we calculate it? So we will see that in the next lectures. Thank you.